Good morning, everybody. Welcome for another seminar at the Instituto de Astrofísica de Andalucía here in Granada, in Spain. And today we will have the talk by Dr. Leonardo Kubelis from the Ludwig Maximilian University of Munich in Germany. And he will talk about LP791-18d, a case of study for outgassing rocky exoplanets. So Fran, please, Fran Posuelo will make the introduction of Leo.
Hello, everyone. Thanks for attending this online seminar. As René has mentioned, our today's speaker is Leonardo Kubelis. He studied physics at the University of Crete in Greece, where he originally came from. He continued his postgraduate studies at the University of Valencia in Spain in the field of the stellar astrophysics. He then moved to the University of Liège in Belgium for 3 years, where actually I met him, conducting modeling for Mars and Jupiter at their atmospheres. Following this position, he was awarded with a NASA postdoctoral fellowship at the NASA Ames Research Center in California for Mars global climate modeling. And currently, he's a staff scientist at the Theoretical Astrophysics of Extrasolar Planets, shared at the Ludwig Maximilian University of Munich. Focusing on the theory of exoplanetary atmospheres. So after these short introductions, Leonardo, thanks for coming, and the floor is yours.
Hello, everyone. On my turn, I would like to thank you, Fran, for inviting me and your colleagues of the Exoplanet group in Granada, Pedro Amado and all the others. I really enjoyed being there 1 month, and apologies for not being in person for this presentation. But it seems that you are full, which is good for you. Let me take this out. So I really had the opportunity this last month that I was there to interact with many people, and we started some projects. And this was the whole idea, to initiate some connection between our exoplanetary working group in Munich and Granada group. And I will say the motivation behind this in a while. But first, let me introduce you our team in Munich. We are a new team studying exoplanets. In the German system, chair means like a sub-department. We belong to the Observatory University of Munich, which is the traditional observatory of Munich. And we are about the same size like you at EA. And this was a vision of our team leader, Kevin Henk, to bring together a variety of expertise in order to go 1 step further in the study of exoplanets, meaning that after the detection and after the observations of the atmosphere, if we want to really understand exoplanets as they are real complex objects, and they have many different physical processes from interacting with space and to the interior, and even their formation affect their life. This is a highly interdisciplinary field. That's why you see here all of us, which are on plane expansion right now. We are 10 people, what we are contracting even more right now. And you see here profiles that they are totally different to each other. You see from, of course, exoplanetary atmospheres, to chemistry, geochemistry, to astrochemistry and machine learning, and of course, observational astronomy. But out of 10 people, 9 of us, we are doing theory. And you see that we actually need interactions with people doing observations and data analysis. And that was one of our main motivations of contacting my colleague, Francisco Pozuelos, who is pioneer in detecting exoplanets and knows the exoplanetary demographics and populations. So as you see here, with this variety of people, which come in from totally different fields, it's even, in the beginning, was even very difficult to communicate to each other, not even starting doing projects. So I think it's a bit interesting to tell you a few more details on how we proceed. As some of us, we have teaching duties in the university, in the Master of Astrophysics. We organized master courses each one in its own field. We have these 3 to 4 right now, which what happens is most of the times we have more researchers than students. And this is just to train ourselves in order to be able to interact to each other. That's how this interdisciplinary, how difficult it is to work in this field. Yeah, you see here these different courses. And for example, geochemistry, it happens that also in Munich, there is a very strong team of volcanology, which is world famous. And we have a lot to learn from them. And many times we bring lectures to do the lectures of the course so we can learn from them. And of course, in the Bayesian inference, which as maybe you know, it's very important in data analysis in our field. We learned that from the cosmologists, which have already working decades with this Bayesian statistics, and this machinery is very mature on their field. Another thing is that we are organizing summer schools. We had last year a summer school on high resolution spectroscopy. And this year, this summer, we are organizing one which we call it Geoastronomy, and it's basically how we can apply geosciences to rocky exoplanets. And now, after this, okay, let's go to science. This is the exoplanetary demographics. Every exoplanet talk I have been so far, it starts with this plot, so I will do the same to keep the tradition. You see here all the exoplanets. Well, actually, this is out to date. This is a plot from last year, but we know of about 5,500 exoplanets today. And the first thing one observe when you see these plots, and if I overplot the planets of our solar system, are two things. The first thing is the clear dichotomy in our solar system between the rocky planets and the giant gas planets. And the other thing is that actually in nature, you don't have this dichotomy, but there is a continuous production of planets, meaning that nature can produce all sizes of planets, from small rocky planets to giant planets. And note that I'm not talking about the statistics and this famous radius valley around here. I'm just saying that in nature, you can have all types of planets, from very small to very giant planets. The second thing, okay, is this observational bias that all the planets are close to their host stars, just because it's more easy to detect them. So if you want to learn more about these exoplanets, and they are very far, we cannot send any probe there, of course, like the planets in our solar system. We have to do it observing their atmospheres. Now, if I summarize this field, which is called exoplanetary atmospheres, I can very simply, in a very simplistic way, summarize it in this cartoon here. All we want to do is taking observations, which we actually do. We have about 2 decades of doing observations of exoplanetary atmospheres. And recently we have this James Webb Space Telescope, which we can actually go and observe smaller planets with much higher quality. Then based on these observations and having some kind of a priori guess or knowledge of what their physical processes might be, we can inverse the problem by applying forward models and actually obtain what their actual nature is and learn a bit more things. The last step is to make the interpretation, to actually understand their climates, their environment, their formation histories, etc. So we cannot go to this last step if we don't pass from the first 2 steps. The thing is that, okay, we have done this exercise for many years for the giant planets, and just because they are easier to observe. And actually, they're, by coincidence, much easier in their structure, in their chemistry. And I will say more in a bit. But even this first step to make the retrieval process still is not 100% sure, not even for the giant planets. And the problem is not the machinery, I mean, the math itself, how does it work, but there are 2 main problems we have there as a field. The first is that We don't know how to, in an optimal way, to apply these techniques in our field. For example, how the errors are propagated or how to compare models to each other. For example, if we want to make a retrieval with 6 molecules or with 5 molecules. And the second, which is the most important, actually is a bit worrying, is that all our forward models that we are applying to this retrieval processing they are not suitable because, as we said, the planet is a real object, 3D object, very complex. And we always apply something very simplistic. And the reason is just it's computationally very expensive to do that. But there are many people working on that, and we're having progress, but slowly. The thing is that if we don't solve this problem to the more simple planets, it's very difficult to go deeper in smaller planets. And saying this about observations, just to summarize again, we first observe planets that are very hot and very big. And the reason is that, and I will say a few details later, they have, in one phrase, they have more pathy atmospheres. So they block more light from their host. But recently, with better telescopes like James Webb, or in the future with these large telescopes that they're building in Chile, maybe we will go deeper and deeper in that sense. Now, from observations that we have from these giant planets, we were trying to observe, for example, abundances, molecules, and compare them to each other. For example, carbon to oxygen ratios, oxygen to hydrogen ratios. And from this, we could actually learn something about their chemistry, their physical processes, or their formation history. Just because giant planets, they stay the same, they contain their atmospheres from their formation. And this is what we call the primary atmospheres, or nebular atmospheres. And it's mainly from hydrogen and helium. Now, as we go to smaller planets, and especially the example of the solar system, the rocky exoplanets, the theory tells us that their atmosphere evolves from outgassing, means that it's coming from the evaporating magma or volcanoes, right? And this is another dichotomy very clear in our solar system. And of course, what astronomers keep finding in the exoplanet population are not gaseous planets and not very small rocky planets, but something in the middle, like they call it super Earths or sub-Neptunes. And then how their atmospheres are something maybe in the middle. James Webb is recently made observations of sub-Neptune, and we don't have a clear theory, but everything seems that it's something like a hybrid atmosphere. So the question here is this, that how a secondary atmosphere is evolving, and what we can say about, for example, the habitability, whatever that name is, or even the biosignatures in the future, right? Because this has to pass from this exercise. We have to understand what secondary atmospheres actually are. Okay, so let's take, for example, the Earth, right? It's our own planet. We have in situ observations, and we have some better theory. So here I'm showing, let's assume that this was the protoplanetary disk of the sun. At some point, Earth was created, and the theory tells us that the first 1.5 billion years, about something like this, the Earth was in a state of a magma ocean. And then whether it had some kind of a primary atmosphere, very thin hydrogen and helium envelope, it's not very clear. But again, the theory tells us that rocky planets, when they are created, can accrete from the surrounding of the disk at maximum 0.1 of their total mass in an atmospheric mass. And whether this is very fastly evaporated and lost into space is not clear. But in any case, what we understand is that this hot magma ocean is evaporating, is outgassing heavier molecules, volatiles, and enrich the atmosphere with what is called higher metallicity or higher molecular weight. And this second state lasted about 2.5 billion years, if I recall correctly. And then the magma was slowly cooling down, and then a crust was formed, and then the mantle slowly was solidified. Now, what is believed is that life in a bacterial form started either at the end of this second part or within the third quarter that I'm showing you here, and greatly affected the atmospheric composition. This is what's called the Great Oxidation Event. So at the same time, also, there are processes not only on the lower boundary, which is the outgassing, but also on the upper boundary, atmospheric escape, and also a process which is called hydrodynamic escape, which is a rapid escape of gas. And this can also affect a lot the atmosphere, especially losing the lighter atoms like hydrogen and helium. And then the last is that the atmosphere as we know it today, and the stable atmosphere. Now, the question I want to make here is this, that, okay, so we have this evolution of the atmosphere, and we know that in this example from Earth, life greatly changed the atmosphere in its composition and how it looks like in general. If life didn't exist on the Earth, how the Earth would be, and is this some kind of an abiotic baseline for Earth, which means that if I can, for example, from first principles, solve these processes and have some kind of abiotic baseline, then if I compare it with the rocky planets, if I see something that deviates from that baseline, should I start studying it in more depth? Because maybe, for example, it's biosignals, whatever that means at this point. The thing is this, that this problem is very complex. As you see here, nobody have solved it, not even from first principles. And I would say this is computationally cannot be done at this point. So nobody have done it. So what we want to start working is this first part here. We want to find planets that are in a state of a magma ocean or partially magma ocean. So they are partially merged, partially solidified. And we want to solve this exercise. We want to understand how a magma ocean is outgassing and what kind of atmosphere is producing. And at the last step, what kind of observables it can produce. Because, of course, there's no life there, right? Nobody is expecting biological chemistry in 1,500 Kelvin, right? So this exercise has to start like in a simple way. And it has two examples. Let's take one planet that is just formed, and then there is a core which is the melt. It's very hot magma. And then maybe there is some kind of a primordial atmosphere, which in the first case, we can assume, for example, that it's completely lost. And then from this magma ocean planet, there is outgassing. And then we can check what kind of atmosphere is produced there. And then the second example is that this embryo atmosphere is partially lost to space, but there is some kind of a thin envelope, which can call it embryo, hydrogen and helium. And then we can outgas from this magma ocean to this envelope, which will have some effect, of course. So that's the exercise we want to solve. And that's how our collaboration started with IAA. We wanted the best candidates. First, we found one planet to do this exercise. And in the future, we want to find few more in order to see if our results are consistent between different systems. So then, as you see here in this example, what kind of atmosphere you would have in a rocky planet in the beginning, what kind of atmosphere you will create. It totally depends on the melt, right? Because you see here that the driving force that creates the atmosphere it's from the interior, it's the melt. So this paradigm that we had for giant planets of metallicity, etc., maybe we should reevaluate it and think about other parameters that are key in this study. For example, and comes from another fields, like for example geochemistry. And one of these parameters is called oxygen fugacity. And maybe that doesn't mean anything for you right now, but I will explain a bit more later. So then here in this exercise that we did the last month, this is actually work in progress, and what I'm presenting today, it's work of the last month, so it's quite preliminary. We selected one specific planet that was discovered 6 months ago, if I recall correctly. And then this belongs in a system of 3 planets. I think planet C is a sub-Neptune. Planet B, I don't actually remember, but probably a rocky planet. And planet D is the planet that we study, and you see here that it's about the size of the Earth, similar mass, similar radius. Well, the equilibrium temperature is almost 400 kelvins, and they call it a temperate planet in the paper, but you will see that in the simulations that I will present later, equilibrium temperature is just an indication of the stellar flux that reaches the planet and nothing more. Here on the right, the plot, let me explain. In this y-axis, it's a heat flux. And in here, it's the mantle temperature, the temperature that the mantle has on the planet. And then this is the energy balance of 2 different fluxes. One is the tidal flux, which serves as heating. And the other one is the convective flux, which serves as cooling. So this planet here, I forgot to mention that due to the other planets, they estimate that it has a lot of tidal heating effects. So they calculate with a theoretical model the tidal heat flux, and then you can do the same for the cooling, and then there should be some kind of steady state of the planet where these 2 lines intersect, right? The different lines here are just semi-empirical values that they use in their modeling for the material of the mantle. So depending on the material, you would have more heating, more cooling, etc. So there are 4 different scenarios. But the physical meaning is that, okay, if you have such a planet that it's continuously on a tidal heating effect, then there should be some kind of a steady state and then the planet should remain, the mantle should remain in a constant temperature. And then just for comparison, they overplot here the Io, the moon of Jupiter, which is the most volcanic active solar system body. Okay, so that's why we chose this specific example, because we expect with high probability that it will be on a partially molten phase. And on the other side, it's very close to its host star, which means that it should have a very hot atmosphere, and this you will see in a while that increase our chances to observe it. So then what we are trying to do is we want to take this specific example and do 3 different scenarios. We want to model it as a magma ocean. We want to model it as a partially molten magma. And then we just want to model it with a rocky surface, but with high volcanic activity, which means we just inject a lot of outgassing in the system. Yeah, and this is the main physics that we want to include if we want to do such a modeling. We want, of course, to have the stellar irradiation on the top. And on the bottom, we want to have the outgassing, which will depend on the interior, and I will say how in a while. And then we want to do all the processes, thermochemistry and photochemistry in the atmosphere. Now, what we chose to do in the beginning, and we might want to change that in the future as we enrich the results of our project, is we chose to start with a very thin embryo atmosphere, hydrogen and helium. Now, how we do this lower boundary here, the outgassing, how this depends on the interior. So all the model that we are doing here depends on these model inputs, everything, all the chemistry and all the outputs. And this is this, okay, as we said, the stellar spectrum, the surface pressure, we have to prescribe some surface pressure, at least in the beginning. We have to prescribe something which is called oxygen fugacity, and I told you before. In simple words, this physically means the oxidation state of the mantle, or how much oxygen I have in the mantle in comparison with the other atoms. Then there is another parameter here, which is called the graphite activity. And basically, this is how rich is our magma in carbon, because this will create graphite and then somehow will isolate the atmosphere from the magma. That means, in simple words, if I have a lot of graphite, will flow on magma and will create some kind of different interaction with the atmosphere and interior. All of this machinery is based on, well, it's based on geochemistry, and I mean, there is a lot of knowledge behind this. But there was recently a paper submitted by my colleague, Meng Tian, who is a computational geochemist. And what he did is this. He made calculations 0D, which means only an interface, melt and atmosphere in specific pressure. And based only on those parameters that I mentioned to you before, he is able to predict what kind of outgassing you would have. Of course, this plot is kind of messy. I just want to indicate you this. Yeah, first of all, let's explain this axis. Here it's mixing ratios between the molecules. And here is this parameter, which shows the oxidation state of the mantle, oxygen fugacity. Just take that if you have higher number, it's higher oxygen in the mantle. Just this, less oxygen. And then just see that if I have higher fugacity, for example, I will outgas more water vapor in the atmosphere. And the same here, for example, for CO2. You can note those two volatiles for now. So then going back here, the model we want to construct is this. As we said, we want to do the outgassing here on the bottom, which for this, we make an assumption that atmosphere and the mantle is in equilibrium, at least on the first layers, and we will see if this is valid or not. And then once we outgas the volatiles, then we want to solve all the thermochemistry and photochemistry, and this we have to do it solving this chemical kinetics continuity equation, where I here it's a different species, P is the production, and here L is the loss mechanisms, and here it's let's say the mixing and diffusion, which in 1D modeling is just trying to imitate the dynamics. And here is simply the additive transfer equation. So all of this, they have to be coupled together in order to have a realistic simulation, because one affects the other, of course. And then just to mention that is here setting here the interior and the first layers of the atmosphere in equilibrium. What does it mean? It means that if I take this equation here is I didn't explain, apologies. This equation here, it's the Gibbs free energy of the system. So if I have, for example, a system of some molecules and some constituents on the mantle and some others here in the first layers of the atmosphere, if I say that this system is in equilibrium, I just calculate the Gibbs free energy of the system and then minimize it. And that's how I say that. And then suddenly the system is in equilibrium and can directly calculate parameters like partial pressures, etc. Then how does this work? There is this cartoon which explains a bit. So what does it mean is in equilibrium? Simply means that the chemical time step is much smaller than the dynamics time step. So that means that the chemical reactions are so fast that they reach equilibrium before dynamics do any change in them. And then as the atmosphere goes to cooler layers upwards, then the chemical time step will be slower than the dynamics. And actually, you have to treat it differently. So we have to treat it here with kinetics and not with chemical equilibrium anymore. Then we do this. I can give you here some example of how this modeling works. We start with these three parameters. We have to prescribe that. And then we simulate until we reach steady state, right? We use photochemistry. Our chemical network right now is carbon, hydrogen, oxygen, and N, and it contains about 600 reactions. You see here what I was referring before, that this planet has an equilibrium temperature of about a bit less than 400 Kelvin, but you actually see that if we perform properly the calculation, it's much more than that. So you see that whatever habitability means, if you don't do properly the calculation, it doesn't mean much at this point. And of course, there are many unknowns in the system, right? We don't know the surface pressure, so we have to prescribe it. And in this specific example here I'm showing, you see that all the atmosphere is in a gas phase. There are no clouds forming. Now, once we reach a steady state in our simulations, we want to go to the next step, and we want to see how we would see that planet. So we want to create some kind of a synthetic spectra, and we have two types of synthetic spectra. We have the transmission spectroscopy, which is basically when the exoplanet is eclipsing its host star, and by the change of the light, we can measure the spectrum, or the emission spectroscopy, is simply the light that the planet itself emits. So you understand another reason we chose this is because if the planet is hot and also the star is cool, for example, it's an M dwarf, then the contrast would be something that we could actually see. Now, talking about transmission spectroscopy, this is exactly what I was referring before. You see here that every wavelength will create a different size of the planet, so it will block different portions of light. And how different is comparing two different wavelengths. So if we are able to actually detect a spectral signature, will greatly depend on this what is called scale height, which is basically how the density is changing through the atmosphere, and it's coming from the barometric formula. And you can see it here on the bottom. It basically depends on the temperature, the mean molecular weight, and the gravity. So, for example, if a planet like Earth is cool, it has a very high molecular weight, it's practically impossible to detect it with current telescopes. But if we go to a planet which is hot, and basically, well, like hot Jupiter has a very low mean molecular weight, the atmosphere becomes very puffy, as I was saying before, and it makes it much easier to detect. Now, all of this theory, we can derive even analytical expressions about that, and this means that we can control very well what we are doing. Of course, we are not using this, but we are using a more sophisticated numerical model. I'm just showing you this because I wanted to indicate a very famous degeneracy that exists here. Because to create a transmission spectrum, we need to set two parameters. We need to set the radius of the, it's not the radius of the planet, but it's a normalized radius and the pressure at the same time. And we don't know both of them. So we need to choose. For example, here we can set R0 as the radius of the planet as it was given in the detection. But in reality, the detection was made by transition depth itself. So it's very difficult to solve this. So we have to set something here. Okay. Then from this we can create a transmission spectrum like this, which maybe doesn't say much to you, but we were used, for example, a oxygen fugacity of -3, so less oxygen in the mantle, and we created this transmission spectrum, which I can plot it this way too, which is a more explanatory. Here shows the contribution of its sorry, cursor. So here I'm showing the contribution of its greenhouse gas in this transmission spectra. You see, for example, here that the dominant gas is water vapor, of course, but there are some windows here that we can see CO2, like this famous 15 micron or for about 4 micron. And then in the same way, we can take this transmission spectrum and check how, if this was the real atmosphere of the planet, how James Webb would have seen it in a different detectors, which I'm plotting here in different colors. Of course, here the points and the background spectrum are overlapping perfectly because it's the same spectrum, right? But what I want to say is that in this scenario, we could detect the transmission spectrum of this planet. But given that the parameters I set here in this famous degeneracy I was talking before are kind of realistic. That means that if I set the radius of the planet as it was detected from the transmission depth in its detection in the first place, then I have to set some parameter which is not the surface pressure, but so it has to be between the surface pressure that I set in my simulation and the pressure that is not low enough that the optical depth goes much lower than 1 in each of these wavelengths. So it's a bit tricky. So that's why predicting spectra like this, I mean, probably it's not the right way to do it. First thing is to observe it and then try to explain it, right? But anyway, in this exercise, we want to go a bit further, which means what I'm doing is I'm taking different compositions of the mantle, and by changing this oxygen fugacity that I was talking to you before, I'm creating all of these transmission spectra here and see how they affect the atmosphere, basically, or the spectral signature that we are seeing from Earth. Maybe this one is a bit messy and you can see much. So if I smooth it, you see here much better how the spectrum is changing. And one thing we did as an exercise is identify characteristic spectral bands, for example, from plots like this to these different scenarios. And like this ones, for example, those three, which, for example, in this one, only water is dominating, or in the other one, 15 micron, only CO2 is dominating. And check what is changing between these scenarios, these mantle scenarios. And what we have seen is this counter connection, which means that if I have less, let me first explain how we made these points here. So what we did is that we went and we integrate the strength of these lines, similar way as what equivalent width is in astronomy, right? So we just integrate all the surface area on the bottom of the line, and then we normalize it with its medium value just to have the same units more or less, and to see what is changing. So as you see here, the physical meaning behind this plot is this: that if I have a mantle less oxidized, it will the atmosphere at the steady state will have more water than, for example, CO2, right? And then as I'm changing the scenarios in the composition within the mantle, it will be the opposite. Okay, but now this is when I simulate the atmosphere as a total. If you recall here the previous plot I'm showing, only by the outgassing itself, this wasn't true. So what we were seeing before is that both cases you would outgas more CO2 and more water. So what does it mean? It means that when you outgas, these hot volatiles in a non-equilibrium atmosphere, the chemistry and the photochemistry will bring it in a different form, which I haven't yet built such an intuition because we are talking about dozens of reactions, not even hundreds of reactions. But this is something we didn't expect, and we have to explore a bit more. Now, what does it mean practically, right? So imagine I observe a spectrum, a transmission spectrum from this planet. Just by measuring these different bands, maybe I can infer what the mantle composition is just by observing the atmospheric bands, which is kind of important for this type of planets and give us a first step of understanding their interior. Then going a bit farther, we can do the same for we can create synthetic emission spectra. And this is quite a bit more easier because if you remember, we have already done detailed radiative transfer. So we just need to calculate the outgoing radiation per wavelength. And this is simply the contrast. For example, the flux of the planet, we have to compare it with the flux of the star. And of course, this phi is the phase angle, which is when it goes around, we observe different phases of the planet. Now, for the spectrum of the star, we simply observe it when the planet is absent, right? When it's behind the star. This cartoon here shows how we are basically doing the radiative transfer, and at the end we just sum up all the contributions from all the layers in the atmosphere. And then we can create a similar way as transmission spectra, we can create emission spectra. You see here that this is part per million per wavelength here, which is actually something that potentially you could observe with James Webb. And you see here there are also some kind of changes which we haven't analyzed yet, this type of spectra, if we can say something about that. But what we have seen afterwards is that this specific planet was accepted for James Webb observations in the third cycle. So we are waiting for observations. I don't know, maybe in 1-2 years, I'm not sure. But was specifically accepted to do emission spectroscopy. So you see here in this previous synthetic spectra I showed you, this would be the expected cover range of the future James Webb observations, which is actually quite positive. So we can do some kind of a pre-analysis. But So yes. Now, just to make here some conclusions, because as I told you, this is kind of a preliminary. All I presented to you was done in Granada with my colleague the last month, and actually is an initiation of a collaboration between our two groups. We hope to engage with more people, exchange students, etc. And then yes. I think that this exercise we are doing is important because finding candidates which are in this phase of the revolution, it's kind of a primary phase, and then we can directly see a secondary atmosphere on a plane evolution, and we can say, and we can solve this exercise, and actually is in a phase that it's more easy to interpret at this point. And then, yeah, talking about, for example, what biosignatures and whatever that means at this point, I think this is an obligatory exercise we have to solve. Because right now, when talking about biosignatures, we are totally in unknown unknowns phase. We don't even know what to expect. So if we don't first understand what is the abiotic baseline of the planet, I mean, what kind of an atmosphere you can create out of the rocks, simply insane, then we cannot go not even one step further. So I think this type of exercises are really important. And then, yeah, here I'm leaving you with a vision that, as I told you, we cannot go in this, we cannot start talking about biosignatures if we first don't go in this intermediate step, which is just solving the exercises of what is geological false positives. And something else is that, as you have seen, that this is a highly interdisciplinary field. So the vision is that the future generations of exoplanet scientists can no longer be trained only as astrophysicists and not only as geochemists, but they probably have to have some kind of holistic training. So thank you very much. I will leave you with these points here, and I can get questions from you.
Thank you very much, Leo, for this very interesting talk. So now Fran will manage the questions for all the assistants. Please raise your hand, and then Fran will give you the word for questions.
Yeah, yes. Thank you very much, Leo, for this talk. Let's see if we have someone that wanted to ask something. In the meantime, that someone decide to ask something, I would like to ask you about which are actually the most critical points to form the secondary atmospheres, because actually is the main point here, is the secondary atmospheres. So which are the challenges to create them?
Yes. So we need to understand what is basically the bulk composition of the interior of the planets, which is very difficult to do it from first principles, of course. But where the community is looking is this story goes back in their formation history and how the materials that form the planet were cooked on the disk, which means the composition that, for example, planetesimals and other rocks, what their compositions was when they formed the planet will be crucial. What the composition of the planet will be, and then what the outgassing would be. So we have to go step by step backwards. And now what some people in the community are doing is directly looking in the photosphere of the star and check, for example, what is called the refractories, what is the proportion of the refractories, and then try to apply this to the planet as a bulk composition, at least for the interior. And then, of course, is this the volatile ratio, which it's a very difficult problem to solve because within the disk there is a mechanism which is called devolatilization, which means that if you have a rock and you have it in a very hot part of the disk, will by itself outgas, and the volatiles will evaporate, and then maybe they are not in this primary material that will form the planet.
Thank you. Thank you very much. I don't see any question either in the chat or any hand raised. Can you maybe explain more about which is the influence of the star in all these studies? I mean, in the atmospheres and the expected pollution of the secondary and primary atmosphere, and how affects all these computations?
Yeah, I think the effect of the star. Well, apart from all the errors that can reproduce in the observations, it's what I told you. They will basically, if we observe the star, we can learn something about the primary composition of the disk, and then But this is very difficult. This is a very difficult exercise.
So no easy connections.
Yeah.
Okay. Okay. Thank you very much. I don't know if there is not any other question. Okay. Manuel has a question. So Manuel, go ahead. Thank you.
Oh, hello. Good morning. Well, first of all, thank you very much, Leo, for that very nice and comprehensive talk. It's a global view. Two very important ideas that you put forward. One is how can we learn about the planet evolution, the planet formation, just for looking at the atmosphere is a key point. And the other, the one comment you did at the end about that we need really many people expertise in many fields to understand everything. But anyway, my question was about a specific. This is one of the results that you found that was, which I didn't follow very well. Is it about the water vapor bands versus the what's it called, the other, the oxygen fugacity? Oh, that's one.
Yeah.
So I the different line, the different color there, because I read on the left the water band.
Yes. So this is yeah. I could have plot here only one, the blue, or only the yellow. It's just these bands here indicate how much water you have in the atmosphere.
Right.
And then it tells you that, and this x-axis here, it's basically just a parameter that tells you how much oxidized is your interior, your magma.
Okay.
Yeah, so then this plot connects these two things, connects the final state of the atmosphere that you observe and the interior of the mantle of the magma, which means that if this is at least true, this exercise that we did, then maybe you can go and observe the atmosphere and say, okay, look, my water, for example, content, my CO2 content, or this CO2 band in comparison with the water band, it's like a calibration, and
Okay.
then you can say something about the interior. I mean, how much oxidized is this magma?
Yes. Okay. So just by the ratio of the band, is it done by transmission?
Yes, this is transmission. Yes, exactly. So you see, for example, here in this plot or in this plot, all of these transmission spectra which are synthetic, right, came up from different interior composition, so interior chemical inventories of the mantle, and then the spectra came up from the final state of the atmosphere. So what kind of atmosphere will my interior create? So we take different scenarios and we say, okay, in one case will be this, in the other case will be that. And so it's kind of a connection between the interior and the atmosphere.
Okay, good. But how far are we for detecting them with the real James Webb spectra?
Yeah, so here, for example, in this prediction here I did, I mean, if we take transmission spectrum from James Webb, only one transit, in theory, we can detect it. If, for example, in this condition if the surface pressure is at least that of Earth, but then, it will be very hot, etc., and then it will be, so you could detect it in theory. But right now, there is no proposal with James Webb to observe this planet in transmission, but only in emission, I have seen here.
Right.
And in emission, I can understand why, because it's actually, it could be actually quite bright, so they could detect it.
Yeah.
So they plan to do about, I don't know, 5 observations, I see here, if I understand this correctly.
what is really new for me, because so far I had that we really need a lot of transit in order to get a signal in order to, I mean, those planets have a very compressed atmosphere, so the signal is expected to be very small. So I thought it was really very difficult to get that with a very few transit.
You might be correct, as I'm not an observer, but I try to do this exercise with online tools they have for, with James Webb.
Yeah.
You put your model atmosphere and then it spits back to you how it should be observed. For example, with one transit, with two, and you set, for example, in that case here, I set the noise floor in 20 parts per million, which is it's an optimistic, but I think that's about it, right? I don't know. If someone knows better this instrument, can jump in and correct me.
Okay. Wow. That's really impressive. Thank you very much.
Thank you. But one thing that we have here limitation is the upper boundary, which is the escape, as you know much better than me, because it's a crucial parameter for the evolution of these planets, especially small rocky planets, because they don't have much gravity to retain their elements.
Yeah. Okay.
Mm-hmm.
All right.
Okay, I don't see any other question from the audience. So from my side, I think we are okay. I don't know, Rene, if there is something else to do before to finish, or Leo wanted to say something before to finish up.
No, thank you very much for inviting me. I really enjoyed the whole visit, the city, and I don't know. I wish I come back soon. Thank you. Bye-bye.
Okay, thank you very much, Leo. Thanks to all for attending. It's time to lunch, so we let you escape to have some meals. Okay, thank you very much for everything. Bye-bye.
Bye-bye.
Okay.